Hi, welcome to Unit 67. This is basically how massive stars end their lives, or they end basically, how they die. So we're going to describe the end stages of a massive star evolution, sketching this through the HR diagram. Also, we're going to list the elements fused in a star core and explain the endpoints. Basically, at some point, star cannot fuse anything past basically iron. That's the last element the star can make. And then we're going to describe the events or the causes and events of a star core collapse and how this produces gamma ray bursts in the most massive stars, and describe the supernova remnant, indicating which elements are uniquely found in it. Okay, so you're asking what if there is anything, how come we have in the periodic table elements heavier than iron? Well, in this case, here is probably the role of the supernova. A lot of these ideas, by the way, are being revised further because now we know that neutron stars can collide and produce heavier elements. As a matter of fact, the new tendency is that gold, for example, and heavier elements are produced only through this process. Okay, neutron star collisions. Okay, and hypernovae, and also some of these gamma ray bursts are coming probably from this type of interactions. Anyway, so let's not. So this is in a nutshell how the massive star will evolve. It takes only a few million years to basically go through the entire lifespan. Again, remember in few units we saw before that the lifespan of a star depends on its mass. The more massive stars, the less their lifespan is, and this is the typical stage of that. So it has a main sequence stage that lasts for a few million years. Then it's going to go through a blue supergiant stage, where it's going to be fusing hydrogen in its shell until the temperature becomes high enough so that actually the helium that was formed in the core starts fusing, and that's going to basically once it starts to run out of that, it's going to continue burning or fusing hydrogen in its core, in its shells, and the layer of helium now starts to be immediately under the layer of the hydrogen. Then it's going to start, the temperature starts to increase because of the further collapse, because it's running out of fuel, to the point that it starts fusing carbon, neon, oxygen, and silicon into heavier and heavier material, until at some point it's going to produce a iron, in which case it cannot do anything with it, because you cannot fuse hydrogen and expect to form energy to maintain that hydrostatic equilibrium. So there is no more hydrostatic equilibrium. The star collapses in itself, and the supernova happens. And this, like I said, it's only a few million years, the whole process. Okay. So again, this is a description of what I was talking about. Carbon is left in the so basically now there are shell, like an onion shell, basically different shells starts to form from the core out. Okay, being the newer elements are still in the core, and the little older ones they're there, and the even older ones they're on top, and so on and so forth. Okay, so here is a table that gives you an idea about what process, what temperature is needed to include what process. Few million kelvins, like for example what's going on inside the core of the sun, is enough to trigger the proton-proton chain. Okay, so basically 4 protons forming a helium atom, and that's high enough. And for a massive star of the size of, again, when I was saying massive stars earlier and gave it a number for its lifespan, it depends really on its mass. So these numbers in here are for a star that is 25 times more massive than the sun. Okay, so that process takes about 7 million years. 7 million years. Okay, that's nothing compared to like the sun, which is 4.5 billion years in its age already. Then for about 700,000 years, not even a million years, the temperature would be high enough to fuse three helium atoms, or helium nuclei, called alpha particles. So 3 alpha particles forming carbon 12. Okay, and the temperature required for that is about 100 million Kelvin. Now, it turns out of material is going to collapse further. Its temperature increases to the point it reaches 200 million Kelvin. It doubles in temperature. That also lasts about 700,000 years. and that's going to actually fuse the carbon with the helium, forming oxygen, the normal oxygen. If the temperature, because now it's running out of carbon in its core, so what it's going to do in here is going to further collapse until its temperature reaches about 600 Kelvin in the core, 600 Kelvin, 600 million Kelvin, okay, sorry about that, and for about 300 years. That's nothing. For a star, that is absolutely nothing. It's like, just like that, okay? 300 years is nothing, 3 centuries. It's going to fuse actually carbon and carbon. So it's going to fuse carbon forming neon and another alpha particle, okay? Now, if 300 years is nothing, compare that to 8 months. For 8 months, it's going to fuse the neon and form magnesium and oxygen, okay? But the temperature for that is 1.5 trillion Kelvin. So the collapse must have been so much now of the core that its temperature went up to this point in here, okay? And that's 8 months. It's nothing. 8 months is nothing for a star. It's actually even nothing for a lot of the events in here, okay? And then transfers of neon, so it's going to start fusing oxygen, but that requires temperatures of about 2 million Kelvin. Again, because it's running out of fuel, of neon, so it's going to collapse further, increasing its temperature. Once the temperature is about 2 billion Kelvin, then for about 3 months, which is absolutely nothing. It's like a fraction of a second for us, okay? It's going to fuse the oxygen and forms a silicon. Then that silicon is going to fuse when the temperature, again, we're running out of oxygen now in the core. I mean, it moved, so the oxygen has moved to the shell because there is nothing in the core. The core is still collapsing. So in this case, the temperature increased to about 2.5 billion Kelvin in 1 day. Can you imagine that? In 1 day, a fraction of a day actually, all of that silicon in the core will be converted to iron. And that's the end of it. There is no more collapse of a core to increase the temperature to cause the iron to fuse. You can't fuse iron. I mean, you can, but you need more energy than you go in. In other words, there is no way you can get energy out of this process to maintain the star from further collapse. It's going to collapse further, okay? So it's like a shell structure, like the onion, basically I was describing earlier. So in a sense that we have the core, which is iron now. And outside of that, we have the silicon layer, oxygen, neon, carbon, helium, and the outer one is the hydrogen from the previous steps. So that's basically the entire sun. At this point, you can't fuse the iron. It's not. There is no way you can maintain the star by fusing iron because you need more energy than what you go in. So there is none of that at the star at this point. Okay. So again, hydrogen and helium, they're relics from the Big Bang in the portions of probably 3/4, not probably, they are about 3/4 and 2/4, 3/4 and 1/4, 3/4 hydrogen and 1/4 helium. And then the star starts to form the other elements. A star like the sun cannot form more than the carbon or oxygen. A star like this one can form all the way to iron, at least through the nucleosynthesis in this process I was describing earlier. So in order to produce heavier elements, you need something else. You need supernovae. Here is basically the periodic table. So we're good up to iron. Iron 56, that is the isotope 56, with 26 protons in its core. But that's basically the end of it in terms of the periodic table as far as the stellar processes. You need to go beyond a star to form the rest of the periodic table, including heavier and heavier elements like nickel, for example, which is next to iron in the periodic table. Okay. So there are several types of supernovae. The one that basically here is the process. Now iron has formed. Okay, the star is further collapsing. And as it does, it's going to push the electrons inside the iron itself. Okay, remember iron is 56. It's really at this point ionized, but the temperature is so high that it's going to push. Not the temperature. The pressure is so high that it's going to push and overcome that temperature. It's going to push the electrons into the nucleus. So imagine with me, you have 26 protons. It's going to push 26 basically electrons. Now the atom is neutral, but those 26 electrons, they go in. Each and every one of those electrons will interact with that proton and basically form in the process a neutron and a neutrino. That's the thing in here, okay? The nuclear reaction requires the formation of a neutrino because the nuclear reaction is not balanced if only the reactants are a proton and an electron. Proton is of a type, in nuclear physics, they call it a baryon, and electron is of a type lepton. So those two types, they meet together and they form a proton. A neutron. Neutron is similar to the proton. It's also a baryon. And it has a zero charge. So you start with a proton that has a positive charge and an electron that has a negative charge, and they fuse and they form no charge. So this reaction is balanced in terms of its charge. Start with positive and negative, and they cancel out. They come out as a neutron. It starts with a baryon, which is one proton, and ends up with another baryon, which is a neutron. But there is a problem. It starts with a lepton, and now you don't have anything on the other side. A neutrino must come out on the other side to balance this one in terms of the so-called the number of leptons. And actually, you can check that this reaction actually produces produces that type of particle. Why am I saying that? Because those ejected neutrinos, they have no charge, number one, and they have extremely low mass, so they don't interact with nobody, so they come out unimpeded from this process. They come out completely, the huge number of them from that. Actually, as a matter of fact, they represent 99% of the energy of the supernova. So the explosion, the fire, the light that you see from a supernova, which is really massive, is only 1%. The other 99% is carried out by the neutrinos. So the gamma rays that come out, which is tremendous amount of energy that can cause all kinds of things, the light that come out represent 1% of the total energy. The other 99% is carried out by these neutrinos that come out unimpeded. Okay, so that's actually one way of detecting supernovae, because just before the explosion, as the neutrons are being formed inside the core, as the material now is collapsing on itself, the products of this reaction are coming out, neutrinos. Some of them are actually going to interact with those materials. So now the material that is collapsing is going to hit the structure, which is a neutron star, and it's going to bounce off, and the falling material that is coming in, the temperatures that are involved are so high that actually that forms an explosion that fuses now iron, that fuses heavier element. So we're talking about tremendous amount of temperature that can fuse even iron at this point, produce heavier and heavier elements at this stage. That is the source of the periodic table. Okay, so the first indicator that we're about to witness in a supernova is actually the neutrinos that we detect. That's why the scientists are building all kinds of neutrino detectors all around to see, for example, to study, among other things, supernovae. So once you have a burst of neutrinos coming from a star that we know is going to go supernova, then we can just put our telescopes and watch the show, okay, that the supernova is going to happen, okay? This is a type 2 supernova, core collapse. Okay, as opposed to type 1a supernova, which is a white dwarf with a companion star. It starts to basically take some of its materials from the outside of that star until it grows and reaches a certain limit, which is the 1.4 solar masses. At that point, it's going to go into a supernova stage. Okay, so that's type 1a. Type 1b and type 1c, and they all have to do actually with how much hydrogen. Remember, in the type 2 supernova, all of the hydrogen basically is gone, with the exception of the shell that has formed. So depending on the quantity of hydrogen, we have different types of supernovae. And for this one, type 1a, you will have a lot of hydrogen in them. So this is the typical supernova and how it's patterned in terms of its luminosity. It's going to peak, and then it's going to fade over, a year or so. Okay? At some point, they're not going to be visible, okay? So that's how supernova are. Obviously, the remnants, including among other things, this galactic cloud that forms around it. Okay, so that's the what the supernova is basically. And inside the core of it, so probably you will have a neutron star. But if that neutron star is too big, then that could collapse into a black hole. Okay, so this is the type 2 supernova. This is the core collapse for a big star. It's going to form a neutron star inside the cloud that basically is going to be ejected and produce all kinds of elements, heavy elements in the periodic table in the process. But that could, if the neutron star is massive enough, then it could actually lead to a black hole. Okay. I mentioned briefly hypernovae in the introduction. Okay, and the gamma ray bursts. It's really under study right now, as I said before, and this could be to again core collapse into a black hole, or actually due to a neutron basically collision that also could lead to a gamma ray bursts, and that could also lead to hypernovae forming more materials, including, as I mentioned in introduction, gold. Okay. So this is basically how the process of gamma ray bursts, GRBs, and hypernovae. Thank you.